Thank you for your introduction, everyone. Hello, everyone. My name is Francesco Tesolin, and today I will talk about my research project, which is PLL arrays for phase noise reduction and beam steering. It will be a little bit more technical than the previous one, so I hope that you can enjoy it. Okay, this is the outline of the today's presentation. After a brief introduction on the motivation behind this work and an overview of the prior solution, we will look at the PLL arrays as an aim to reach local oscillator with ultra-low phase noise performance. Then we further exploit the concept of PLL arrays for a phased array application, and finally we'll draw the conclusion. Let's start with the motivation behind this work. In figure, it is shown the typical architecture of a transmitter. The baseband data stream, it is up-converted through a local oscillator to the desired RF channel. Modern systems, in order to increase data rate, use high-order constellation diagram, such as 256 quadrature amplitude modulation. However, practical system exhibits some impairments, some non-ideality, and in particular, the local oscillator phase noise limits the quality of the transmitted constellation diagram, degrading its AVM, and then which causes an error on the transmitted received signal, and so limiting the achievable data rate. Nowadays, all the local oscillator in practical systems are implemented through the phase lock loop architectures, which is a negative feedback system which allows to generate a gigahertz carrier starting from a clean reference clock source in the range of the megahertz. Typically are employed digital PLLs since they better scales with the advancement of technology nodes and allow to save area and power. In order to minimize the phase noise of the local oscillator, basically we have to lower their main contribution, which is the reference noise, here in blue in the figure, which is caused by the divider, the phase detector, and the loop filter, and the other main contribution is the oscillator. While for the reference noise, there is not actual theoretical limit, you can increase your power consumption in order to lower the noise. For the oscillator, this is not possible, and there is an optimum limit when you can achieve improvement. If we look how they are implemented, the DCO in PLLs, basically they are implemented with a LC parallel tank resonator and a transconductor which sustain losses. The inductor is made by a metal loop realized with the top metal of the technology, while the frequency is tuned by switching some switchable capacitor cells. In order to reduce the phase noise, you have to optimize the quality factor of this resonator, so you have to limit the series resistance here in the model of the parallel tank resonator, and then lower the value of the inductance. However, this process of optimization has some limits, because the quality factor at the end is limited by the technology, and the value of the inductance depends on the area of the metal loop. So in order to reduce the inductance, you have to shrink the area of the inductor, but at the end, you end up with a practical limit that limits the minimum phase noise that you can achieve. To overcome this limitation, in literature, an interesting approach has been proposed, which is the multi-core DCO topology. If you connect in parallel different LC tank, you can create an equivalent tank model which has the same quality factor in principle and an inductance which is n times less, where n is the number of core employed, allowing you to reduce the phase noise by n. However, even if it seems promising, when insert this topology into PLLs, it exhibits some drawbacks. At first, the coupling network between the cores produces losses, as well the resonant frequency mismatch between the tanks causes phase noise degradation. And furthermore, when you implement this in digital PLLs, the large amount of tuning bit required to connect all the cores limit the maximum number of cores that you can employ to 2 or maximum 4. For this reason, in our research, we looked for a different approach. Instead of using multi-core DCO, we consider as the local oscillator output the sum of an array of independent PLL, each of them connected to the same reference clock. Since all the PLLs are independent, with the uncorrelated noise source, the signal-to-noise ratio at the combined output improved by n, where n is the number of core employed. Since in a digital PLL, the main area and power dissipation are associated to the DCO. By moving from the multi-core DCO to the digital PLL arrays, the area overhead is minimum. However, you can fully optimize each of the single core because it's now independent and does not present any coupling components between them, allowing you to extend this architecture for an arbitrary number of cores. Based on this idea, we implemented a dual-core digital PLL array prototype in the 20 GHz range. Then, to ensure that all the output are in phase at the combiner, and so ensure in-phase output combination, we added an offset detection circuit, which basically senses the phase shift at the combiner input and acts a correction with the DTC already in place in the PLL for fractional operation. This is the implemented chip. We implemented it in a 55 nanometer by CMOS technology. You can see from the dye micrograph the main LC tank resonator, and also we extract the second harmonic in order to simplify the DCO design from the resonant tank, and we provide it to the output combiner, which then drives the measurement pad. The measurement results confirm our theory because by doubling the number of active core, and so by increasing the total power consumption from 18 to 37 milliwatt, the phase noise actually scaled by 3 dB, confirming our theory. Comparing this prototype with other state-of-the-art work, we can achieve the lowest phase noise at 1 MHz offset due to the independent optimization of our architecture. Once we prove the capability of the digital PLL array for ultra-low phase noise generation, we move then to further exploit the potential of this architecture in phased array scenario. In figure, it is shown the typical transmitter architecture, which implements an omnidirectional antenna to illuminate the nearby receiver. However, when you operate this architecture in modern standards at millimeter wave frequency, the path loss becomes dominant, which limits the communication distance. For this reason, nowadays, modern transmitter employs the phased array architecture, which consists on an array of antennas which produce a more focused beam, which allows that for the same transmitted power to reach longer distances. However, due to the nature of very focused beam, you need also to steer it in order to reach all the targets on the communication scenario. And to do that, a phase shifter is placed along each antenna element. According to the location of the phase shifter in the signal path, several architectures have been developed over the air. The most simple one is the RF phase shifting, where the phase shifters are placed on the RF path of the signal chain. However, this architecture, despite its simplicity, has some drawbacks, since both the signal distribution and the phase shifter need to go RF frequency, so at very high frequency. In order to relax the phase shifter requirement, the local oscillator phase shifting architecture have been proposed, moving the RF from the RF to the local oscillator path, the phase shifter. However, this architecture still presents some challenge because the local oscillator is still a signal with high frequency that needs to be routed. For this reason, we try to improve this architecture, and we ended up with the localized low phase array approach. Instead of using phase shifter in the local oscillator, in the local oscillator path, we replace it with a LO phase shifting element, which basically are an array of digital PLL with phase shifting capability, each of them connected to the same reference clock. In this way, the only signal that needs to be routed to each of the elements is the reference clock, which is a signal with low frequency and easy to distribute. Furthermore, being each of the elements independent with uncorrelated phase noise, the over-the-air combination of this signal leads to improvement of the phase noise by n, where n is the number of core employed. In order to provide phase shifting capability to the digital PLL, we added a new signal, which is called phase control word, which is basically differentiated as sum to already present frequency control word. Anytime the phase control word exhibits some change, a pulse in the frequency control word appears, and then after a transient set by PLL bandwidth, the output phase of PLL, it is exactly shifted by the PCW. In this way, we can remove bulky and power hungry millimeter wave phase shifter, and then achieve an high resolution phase shift. Then to basically control the phase shift among the core, you can differentially act on the PCB, since each core is dedicated with a phase control board input. This is the picture of the implemented dual-core prototype, which consists of two PLL, fractional PLL, and an offset detection circuit similar to what we presented before in order to remove skews in the reference clock distribution. Here is the die micrograph of the implemented prototype in a 28 nanometer bulk CMOS technology, where each core dissipates 20 milliwatt power. We then characterize experimentally these architectures. At first, we measure the phase shifting performance with a VNA, showing that our RMS phase error is only 0.76 degree. And then we simulate the over-the-air combination of the noise by connecting each of the two outputs to an external power combiner and then feeding into the phase noise analyzer, showing that our integrated jitter scale from 47 to 38 femtosecond RMS, which basically a 3 dB reduction. By comparing this work with other state-of-the-art work, we can see that our prototype achieves one of the best resolution and one of the best phase error, RMS phase error, without requiring any linearity and gain calibration, and at the same time, by including the power and the error budget, also the LO generation. So, in order to conclude, in this research work, we looked to the potential of digital PLL arrays. At first, as a mean to achieve ultra-low phase noise LO generation, and then to further exploit the localized LO phase shifting architecture and in order to remove millimeter wave phase shifter and achieve very high phase shifting accuracy without any linearity and gain calibration. And with this, I would like to thank you all for your attention.